So in the previous lecture we started having a look at matrices and we learned a little bit about their algebra, including how to multiply them. And in this lecture we're going to carry on learning a little bit more about what makes matrices tick. So we need a few definitions. So the first thing is that if we have a matrix that has the same number of rows as it has columns, then we call this a square matrix. So for example, over here we have a 2 by 2 matrix, that's a square matrix. And obviously if you have a square matrix, then you can multiply it by itself, because you'll have an n by n matrix times by an n by n matrix. So the inner dimensions agree. As we saw in the previous lecture, that's necessary to multiply them together, and you will result in an n by n matrix. So in fact, then you could take that new matrix and multiply it by itself again. So what we have is that if A is some square matrix, we can say A times A, that's defined, and we'll call that A squared. And in fact, then we can multiply A squared by A again to get A cubed and so on. So when you have a square matrix, you can think about having powers of that matrix. Another thing to note is if you have any m by n matrix whose entries are all 0, is called the zero matrix. And it acts a lot like 0 acts in ordinary addition. So for example, if we have some 2 by 2 matrix here and we add the matrix of all zeros, which is the 2 by 2 zero matrix, notice that we get A plus 0, so that's A, B plus 0, which is B, C plus 0, which is just C, and D plus 0, which is just D. So just as in normal arithmetic, if you have 6 plus 0, you get back 6. In matrix algebra, if you add the zero matrix, you just get back the original matrix, assuming that your zero matrix has the same dimensions as the other matrix, so you can actually add them together. And in fact, in ordinary algebra, if you took 6 times 0, you would end up with 0. And if you take the zero matrix of the appropriate dimensions for some other matrix and you multiply them together, you end up with the zero matrix as well. So here we've got a 2 by 2 matrix times a 2 by 2 matrix. So that's going to give us a 2 by 2 matrix. Let's look at the entries. Our first entry is going to be A times 0 plus B times 0, so it's going to be 0. Our second entry will be A times 0 plus B times 0, and if you follow through you'll find it's zeros all through. So our zero matrix really acts a lot like 0 in algebra that we know. There are some other special types of matrices. For example, sometimes we want to work with a square matrix that only has non-zero entries on the diagonal. So you'll notice that all of these are square matrices and they just have entries along the diagonal. Everywhere else they've got zeros. So these are called diagonal matrices, and the thing that's kind of useful about them is they're very quick to multiply. So if you have a look at this one over here, this is going to be a 2 by 2 times a 2 by 2, so we're going to end up with a 2 by 2 matrix. Our first entry is going to be the first entry of the first matrix times the first entry of the second, and then you've got a 0 times a 0, so you have 1 times minus 1. You'll find that the two off-diagonal entries are 0, and then finally for our last entry you have 2 times minus 1. So this will just give us minus 1, 0, 0, 2, minus 2. So if you have two diagonal matrices that you're multiplying together, it's as simple as multiplying corresponding non-zero entries, but only for diagonal. Just as a note, any of these entries which are not on the diagonal you will hear referred to as off diagonal. So there's a particular diagonal matrix that is super useful, and it's really a matrix that acts kind of like 1 does in ordinary scalar multiplication. And this is called the identity matrix. So it's a square matrix whose diagonal is all 1s and looks something like this. So if we look over here, we've got a 3 by 3. Diagonal is all 1s, everything else 0. So if you think about what 1 does in scalar multiplication, if you say 6 times 1, then you just get back 6. Well, here if you take an n by n matrix and you multiply it by the n by n identity matrix, you just get back the original matrix that you had. So let's have a check. This is a 3 by 3 matrix times a 3 by 3. So our inner dimensions agree, so we can definitely multiply them together. And our outer dimensions tell us we're going to have the result is a 3 by 3 matrix. And now notice what happens. If we're working out this first entry over here, it says take your first row and multiply it by your first column. But here we've really just got 1 times 1, 1 times 1 plus 2 times 0 plus 3 times 0, so just 1 times 1. So that's just going to give us back 1. If we look at our second entry in this row, then that says take your first row and multiply by your second column. And notice that the second column will pick out the second element in our row. So you'll end up with a 2, and similarly you'll get a 3. Now when we move on to look at the second row, that says take your second row and multiply it by your first column. And again, the 1 in the first column will pick out the first element. So we'll get our 7 over there. When we look at the second entry in that row, we'll get our -8, our 6, and so on. So what's happened is multiplying by this identity matrix has had exactly no effect at all on our original matrix. We just got our original matrix back. And you can check for yourself, but if you multiplied by the identity matrix on the left instead of the right, you'd have exactly the same thing happening. So you would end up with the same matrix. So our identity matrix really behaves like 1 in scalar multiplication. So if you think about saying 1 times 6, you would just end up with 6. So we've got a 0 matrix, which acts like 0 in addition and multiplication. And we've got an identity matrix that behaves like 1 in multiplication. So the next thing you might want to think about is, can you find inverses for matrices? So in real numbers, we know that if you're any real number other than 0, we can find some other number so that when you multiply u and that number, you get 1. So for example, if x is equal to 2, and I take y equal to a half, then x times y is equal to 2 times a half, which is 1. So for any real number other than 0, we can find a multiplicative inverse, something we can multiply by to get back to 1. So the question that we want to ask is, can we find matrices that do the same thing? So we've got over here, this is our multiplicative inverse. Now in matrix language, we want to find if we have some matrix A, which is, for example, n by n, we want to know, can we find some matrix B, which is also n by n, which gives us the n by n identity? Because remember, this acts like 1. So can we find some matrix to multiply A by so that we end up with the identity matrix? And it turns out that this is where matrix multiplication really differs quite a lot from scalar multiplication. So we've already said that it differs because you must be careful the order that you multiply by. But now it's going to turn out that, in fact, there are plenty of matrices that don't have an inverse. So let's define what we mean by a matrix inverse. So firstly, we can only define an inverse for square matrices. So and then we say that if we can find an n by n matrix such that the product of our matrix and its inverse give us the identity, then that thing is a multiplicative inverse. But notice this little if there exists doesn't always exist. So if you're looking for an inverse for a matrix, the first thing you need to check is your matrix square? If it's not square, then there's nothing you can do about that. If it is square, then the matrix may or may not have an inverse. And we'll talk a little bit about how to check for that in a moment. So let's look at an example. So over here I've got a matrix, which is my matrix A, and I claim that this matrix here, this B, is an inverse. Let's check and see. So I should end up with the 2 by 2 identity matrix. So I should end up with something that looks like 1, 0, 0, 1. That's where I'm headed. Let's have a look and see. So if I multiply these together, I'm going to get 1 times a half plus 2 times a quarter. So that's 1 times a half plus 2 quarters. And if I work that out, that gives me 1. So that looks good. Okay, now I'm going to have a look at 1 times minus a quarter plus 2 times an eighth. So that's minus a quarter plus 2 eighths, and that gives me 0. So that's looking good. And I've got minus 2 times a half plus 4 times 1 over 4. So that gives me minus 2 over 2 plus 4 over 4. So that's minus 1 plus 1. So that's looking good. And finally, minus 2 times minus a quarter. So that's going to give me 2 over 4 plus 4 over 8. And that gives me 1. So here we've seen an example where matrix B is an inverse of matrix A, and in fact matrix A is an inverse of B. So just as you have that 2 has the inverse a half, we also have that a half has the inverse 2. So with matrices it works the same way. If B is an inverse of A, then A is an inverse of B. But let's see if we can always find an inverse. I've kind of hinted that we can't, but let's have a look and see. So if I wanted to find the inverse of the matrix 1, 2, 2, 4, I'd be looking for a 2 by 2 matrix, and when I worked out the multiplication, what I'd hope is that I would end up with the identity matrix. But if you actually work out the multiplication for this A times B, you get 1 times A plus 2 times C, which gives you your first entry here. Your second entry is going to be B plus 2D, third entry 2A plus 4C, and so on. And so if this is going to be equal to the identity matrix, then what I need to have is I need to make sure that A plus 2C equals 1. So I need to have that A plus 2C is equal to 1. And I need to have that 2A plus 4C is equal to 0. But if you have a look at this second equation, if I divide through by 2, then I'm getting that a plus 2c is equal to 0. But I need to have that a plus 2c is equal to 1. And so we can't simultaneously satisfy both these equations. So this tells us that there's no solution, and therefore that our matrix 1, 2, 2, 4 has no inverse. So we're going to look in a little more detail at matrices in a following lecture, because we need to think about, can we find inverses, or how do we know if they exist or not. But for the moment, for the rest of this lecture, I just want to summarize what we know so far about the algebra of matrices. So you don't have to learn this list of rules, it's just worthwhile thinking about them and thinking about which are the same as the rules for ordinary scalar algebra and which are slightly different. So if we have a look, we've got the commutative law of addition, which says it doesn't matter which order you multiply your matrices in. So this is exactly the same as when you're adding normal numbers. And similarly, if you think about adding 3 matrices together, again, it doesn't matter how you add them together. So these are all the same. If you're wanting to distribute a scalar of the matrices, so you've got some scalar times the sum of 2 matrices, you can also first multiply through by the scalar and then add. So that kind of adds exactly like you'd expect. And similarly, if you've got 2 scalars that you're adding together and you want to then scale a matrix, you could first scale each matrix and then add. So this all works exactly the same. And again, if you're multiplying by 2 scalars, then it doesn't matter whether you first multiply by the matrix by the first scalar and then the second, or multiply the 2 scalars together and then multiply the result by your matrix. So far everything behaves exactly like you would expect from scalar arithmetic. Another thing that acts the same, if we have our zero matrix, if our zero matrix has the appropriate dimensions so that we can multiply it together, then it always multiplies out to get us 0 on either side. So notice over here that we are talking about the scalar matrix, the zero matrix. So we're saying this over here is matrix multiplication. On the other hand, so if we think about the scalar 0, so just the number 0, if we take 0 times by a matrix, then we're going to get the 0 matrix. So that behaves exactly as we thought. We've already talked about our 0 matrix behaving as an identity for addition, which means that if you add the 0 matrix to any other matrix of the appropriate dimension, you just get the original matrix. We haven't talked about this, but it makes sense. If you want to subtract, if you want to get 0, so you have some matrix and you want something to add to it that will give you the 0 matrix, well, you just take the negative of all the entries in your matrix and that will give you 0. So this is exactly like scalar addition. If you say 2 plus minus 2, that's going to give you 0. Other things that are the same. So here we're going to be careful. If we've got 2 matrices that are added together and then we're multiplying that by some matrix, you could just multiply by the matrix first and then add, so that's fine. And similarly, if you want to add 2 matrices together and then multiply, you could multiply first and then add. Being very careful here, so I'm going to put a little highlight, that order is important. So it matters, don't just change which side you're multiplying by. And then we've got our associate sort of law of multiplication, which says if you've got A multiplied by B times C, it's the same as saying A times B times C. And also, if you take your identity matrix, it behaves just like the scalar. So the big thing to notice here, which we don't have, which you would have if you were talking about scalars, is that matrix multiplication is not commutative. Multiplication is not so A times B is not generally equal to B times A. You might have special cases where it is, but in general this is not the case. So for all of these that we've seen here, listing 1 through 13, matrix algebra acts a lot like normal algebra. But the key thing that is different here is matrix multiplication is not commutative. It's really important which way you multiply things together. So take some time to just get familiar with working with matrices, and then in the next lecture we're going to talk about how to find inverses.